next we have Joe Zuntz talking about cosmology. Wow, that's a long title. A multilingual Python plugin architecture for cosmology.
Hi, thank you very, very much. Very cool, thank you for having me here, wonderful. Okay, so this is about Cosmosis, which is a cosmology toolkit. And it's work of a whole bunch of people, including all these people down here, and a bunch of standard library contributors as well. Now, if you're like me, a bunch of you are just going to Google this and just ignore whatever I say and just start looking at the repository. So that's the URL, or you can just Google Cosmosis. There's this transband who unfortunately have a single called cosmology as well. So the Googling is quite difficult. Okay, so this is the whole context of what we're doing here is about parameter estimation, parameter fitting, and constraining models when confronted with data. So within cosmology, there's been a standard way of doing this that's been kind of honed over the last 10 years or so, which is now pretty much what everyone does. And that's a Bayesian approach to doing these things has become the standard pretty much. So if you're familiar with Bayes, then cool, you don't need to look at this, but otherwise, all you're doing is combining information from what you knew before you saw the data, which is called a prior, what you learn from the data, which is a likelihood. So the process of doing cosmological data analysis becomes about constructing a likelihood. And incidentally, if you think all this stuff is kind of new and weird and cool and not useful, and what you really want is a single value with some error bars, then you are the stats version of an IDL user. And I can justify that quite carefully in case it annoys anyone. Okay, so there's two parts to doing this. There's evaluating a likelihood. That means saying how well fit a particular set of parameters in your big parameter space is, given the data. And then there's varying those parameters to explore the parameter space. And Cosmosis tries to address both those things and make them a little bit easier to connect to each other. Okay. So here's an example of a likelihood space. This is the Hubble parameter and omega matter when confronted with baryon acoustic oscillation data. So, cool. Okay, so I'll start with kind of varying parameters and how we do the sampling process, or how we explore parameter spaces. So again, there's a kind of standard way people have been doing this in cosmology, and that's called Cosmo MC, which was written more than a decade ago now by my supervisor, so trying to replace it's okay. And it's very powerful machinery. It's very highly optimized, in particular for CMB cosmology. It knows very, very carefully how to sample the parameter space of CMB likelihood. So it's a very, very powerful piece of software. But it's kind of showing its age. It's partly because there's a whole bunch of other, so it's a Metropolis Hastings code, which is the kind of most generic and most simple, and the first thing you learn about exploring parameter spaces if you do this stuff. Since then, loads of other different packages and samplers and methods have come out and been released. You've probably heard of MC. A lot of people have been using that this week. There's a multi-nest people have mentioned as well, population Monte Carlo. There's loads of these methods, and Emily mentioned Cosmo ABC and approximate Bayesian computation. There's all these different things that are coming up. There are also a bunch of simpler methods that those of us who grew up in or studied this kind of work in about 2004-ish don't actually know about mostly, which is like grid samplers, where you just explore a grid of models, which people tend to forget. And there's also people who've talked about maximum likelihood finders. So, despite my snarky comment before, a maximum likelihood point is still a very valuable thing to know about. So the single best fitting model is still very interesting. So Cosmosis offers tries to find a way of letting you access all of these different methods as simply as possible and with as little change as possible between when you want to switch method. So we've collected a whole bunch of samples together, mostly in Python, but not all, and provided a uniform interface to them. So if you want to switch from MC to a grid sampler, it's just a single line or a couple of lines change in a single configuration file to do this, just to switch things around. So that's the idea, to make it as easy as possible to do that. And so there's a kind of uniform way of calling them. In particular, a bunch of these new and very powerful samplers like MC are parallel, and providing a kind of uniform way to access that parallelism via MPI is another thing that we do, try and do very carefully. The other thing is that different samplers produce different outputs and different kind of ways of specifying what they produce. We've tried to make a kind of standardized way of collecting that output and producing it for people, and then of post-processing it. So turning whatever output you get, whether it's from a grid sampler or MC or multi-nest, into actual parameter constraints, histograms and values and medians and means and all those things. Okay. So big long list of all the samplers we have in Cosmosis right now. The starred ones are in development. We're always looking to add more, and it's always great fun to add more, and it's quite easy. So we like doing that. I won't go through them all, but it's great fun. But the idea is that you produce plots like these, so things that constrain some more, 1, 2, or even 3 of the parameters of your model, and try and display the contours that describe what those values, those things can have, and the kind of likelihood of them, posterior of them. Okay, so that's the kind of sampler side of it, which I think is quite important. The other side is, if anything, a bit more of a change from what people normally do in cosmology and astronomy in general, and that's about likelihood pipelines. So, especially in cosmology and in lots of other areas, what you actually have when you calculate a likelihood is a whole sequence of steps. That's usually a bunch of different theory steps when you're trying to predict the theoretical prediction of a given model. And that might start with working out matter power spectra in cosmology and then move on to more kind of complex things that you can get out of that. But it also includes, typically these days, more and more painful, and this is coming out of weak lensing in particular, systematics and statistical errors get very, very complicated. So in lensing, for example, we have a whole bunch of systematics that screw up your theory predictions. And so we also want to try and include those things in a pipeline that's now getting quite long and complicated. So what we kind of said was that we want to try and take, if you try and do that whole likelihood in one big monolithic piece of code, it gets very, very difficult to keep track of what's going on and what's happening. So we really want to try and break that up into smaller pieces. There are a lot of constraints on this. There are loads of different models, so we want to be able to try and mix and match and switch and swap models between each other. We also want to deal with these weird kind of errors, but there's also very strong legacy and community constraints. There's very powerful pieces of software that exist in cosmology to do parts of a likelihood pipeline. So for example, there's things like the Boltzmann codes like CAM that produce spectra, and there's different bits have already been done of this whole process, and we really, really need to leverage that stuff. And it's kind of funny. We work with a bunch of particle physicists who are really good coders for this stuff, and they just said, well, can you not get everyone to use C++? And there was a kind of little mismatch in that if we tried to do that, nobody would use it because they want to use Fortran or C or something else or Python, and then no one would scientists, and then I'd have no job and I'd be homeless, and then these guys would have to go live on the streets. So download my code, or these guys live on the streets is what I'm saying. Okay, cool. So what we want to do is try and take these pipelines that have got really complicated and horrible and long and break them up, tear them apart, and break them into separate chunks, because usually there is a kind of logical, split of these things into different parts. So usually that's do some very basic physics and cosmology, add in, maybe do then have a module doing the particular calculation you're doing for your particular observable, and then maybe add some nuisance parameters, and usually ending in some kind of likelihood, some kind of comparison to data right at the end. So this kind of modular approach to taking a likelihood means taking each chunk of that calculation becomes a single cosmosis module. So that's either a shared library in C or C++ or Fortran, or a single Python module. Isolate all those modules from each other. The only way any of these modules can learn anything about what's been calculated before them, or save anything for other modules to use, is via an API. So I have an API for saying, here is what I've calculated, here is what I need to calculate it. And so saving and loading becomes a kind of atomic thing. And if you do that, it means you can replace these modules. So you can say, okay, I'm sick of this particular model for my systematic, or I'm sick of using this Boltzmann code, I'm going to replace it with this other one. And you can be sure that the interface will be the same. And if it's not, then you'll get a helpful error message saying you didn't calculate the luminosity distance to the source, or something like that. For new code, obviously, you can just write that interface fairly simply. For legacy codes, it's a relatively simple interface file, usually just a few hundred lines, connecting a legacy code to the cosmosis system. And that usually involves just, load omega matter, load h naught, blah, blah, blah. So this is optional. You can totally just have a single module doing all the physics and all the likelihood calculation, and some of the most important modules are like that. But this approach, as well as, independent of cosmosis, I think it's a very powerful approach to doing likelihoods, because it means you can mix and match and replace and make cool graphs like this, which show the kind of flow of information within the theory of your problem. Cool. So the advantages, it makes it very easy to compare and contrast models. So if you want to kind of replace bits of the calculation and do, say you have a variant model. So for example, if you're into modified gravity like I am, you can replace just part of it without having to recode the whole thing completely. It's very, very helpful for, if you're doing high precision stuff, verifying and debugging bits of code individually, because you know exactly what inputs they have and you know what outputs you want. So you can compare, and you can use that comparison to compare to existing modules, or you can debug very, very much more easily, I think. And you build the pipeline at runtime. So if you're doing, the recent Planck papers had hundreds of different chains that they ran. And they will have had to recompile a whole big code for each one of those models that they used. It must have been pretty painful. Or not quite all, but a big chunk of them. And the goal of Cosmosis is to make that not a thing you have to do. You have all of cosmology in a directory, nearly, and you can pick which of that pipeline you want at runtime. So that's the idea. Lets you mix languages very nicely. So one language can be in C, and so you can do the kind of very slow parts in C or Fortran or something, and then switch to Python for the kind of fiddly but relatively fast pieces in particular. That's very, very useful. You can also share code more easily. It's much easier to publish a kind of self-contained module for somebody, and you know, on GitHub or whatever, and say, hey, use this, and people can slot it into their code much more easily than if they had to merge bits of code together. And you can also automate credit and citations. So whenever you post-process Cosmosis output, as well as generating the plots, it will say, here are the papers you need to cite when you publish this paper. Okay, so that's the big picture. There aren't many places where you can kind of geek out and do implementation details. This is one of them. So I'll do that. And this is hopefully, if you're not in cosmology or you don't care about this stuff at all, this is the bit you should potentially do if you're into using Python with C or Fortran. So there's two ways that C and Python need to interact here. One is by Python needs to load and run C and C++ functions and modules. And the other is Python needs to call a C API to read and write data. There's a bunch of choices for this. Cython, Swig, Boost, CPython. We went for none of the above, and we went for the kind of low-level interface in Python, which is the ctypes module, which is in the standard library, and numpy.ctypeslib. And I'm going to claim that that's for 90% of the things that astronomers and cosmologists want to do. This is a much better solution than any of these, because these are complicated and they're fiddly. And here you just write what happens, and you know, if you know what a library is, this is a much easier approach to doing this, I would claim, but I'd love to chat about that later if anyone wants to. So there's a standard, so the way you specify a module is very, very standard and structured. So you have a couple of functions that you have to write. You have to write a setup function that called the beginning, an execute function which says, hey, you've got new cosmological parameters or new usage parameters or whatever. Let's run and produce your output. And they don't look at that, but it looks like that. And there's a bunch of native functions in Fortran 90 and C to read and write data from this data block. And compiling a shared library that you can open with Python is really, really straightforward. You just have to add a couple of command line flags, and then actually doing the opening and specifying a thing is really straightforward as well. And you have to do something akin to this if you're going to use Cython as well, but it's not kind of scriptable in the way, as far as I know, in the way that Python, you know, this is a kind of lower tech version of the same thing, and I think it's very easy. Okay, so installation's a pain in the arse. So we've got loads and loads of, when you collect together lots of people's modules from different places, they have loads and loads of different dependencies. Someone wants to use GSL, someone wants to use LAPACK FFTW, blah, blah, blah. It quickly builds, you know, very, very quickly. You can always do that manually, and maybe that's for depending on the crowd, that might be easier for you if you're an expert in this stuff anyway. But there's also an installer which works on Mavericks, not quite Yosemite yet, and also SLF, Red Hat, all those things. It's based on the UPS package manager, which is not actually very good, but it's what people in our group knew about, so that's what we do. And it installs everything down to the compiler, all the way up, the whole stack of stuff. And some people react to that by saying, that's horrible, I hate that. And some people react by saying, that's the most useful thing I've ever heard. I don't have to mess about anymore. So it's a very, very bimodal distribution. Any guesses what the single most difficult thing to install with this system is? Mike, any guesses? no, matplotlib is absolutely frigging horrific to install with this approach. Abort Trap 6 has become this like nightmare I have now. Okay, so that's the end. That's a very quick overview. So a couple of outstanding questions. If you have a cosmology likelihood, if you work in cosmology, or even if you're in a different field but you do something sort of akin to this about building a likelihood pipeline, we would totally love to distribute this with our kind of standard library of cosmology code, because we have a growing library of things that are, you know, come with Cosmosis, batteries included. So whether that's physics calculation or a cosmology likelihood, or open some issues if you have trouble installing and so whatever. Open issues really, really welcome. Any kind of contribution, really fantastic. I also have no artistic skills whatsoever. So if anyone can do a better logo than those. So someone yesterday offered a bottle of wine and raised the stakes. I've only got cash. But I'm willing to pay a small amount of money as well. Thank you very much.
Okay, thanks, Joe. So who has any questions for Joe?
So is this cosmology specific? Can we equally use it for non?
No, not at all. So the standard library of codes that we package with it is cosmology specific, but the actual structure and the baseline, the core code is totally agnostic, and it's been used for particle physics as well, actually. So no, you can, if you're building any kind of pipeline, it's the same. Yeah.
Is the installer, I guess, installing just as if you had done ./configure make install? Is it using all of the default paths and everything?
No. So the idea of UPS is that it's relocatable. So the idea is you can just move everything around. So actually, UPS says, and it's also designed for supercomputers where there should be one central location with everyone's packages in. So it just says, it actually downloads binaries for most of the packages. So it doesn't compile GCC from scratch or anything. It just downloads binaries. So.